Hi, welcome back. This is for all the students who missed lessons for their Gordonston weekend. This video is all about Newton's second law. Newton proposed 3 laws of motion. Law 1. If the forces are balanced, nothing can change. If an object is stationary, it won't move until a resultant force acts on it. If something is already moving when the force is balanced, it will continue moving at the same speed in the same direction. Well, that is until a resultant force comes along and causes a change. Law 3. When forces are balanced, that's because there are a pair of forces acting, the action force and the reaction force. These forces are the same size, but they're acting in opposite directions. So, Law 1 and Law 3, they're both about balanced forces, situations with zero resultant force. But Law 2 is all about resultant forces and the relationship between resultant force, mass and acceleration. Resultant force is measured in newtons, the mass in kilograms and the acceleration in meters per second squared. Okay, it's time to practice. Grab your pen and paper. I want you to practice showing you're working out with this question. It's not a trick, it's really straightforward. Pause the video and have a go. So here we're trying to find that resultant force. We know the mass is 0.2 kilograms and the acceleration is 4 meters per second squared. So using F equals ma, we need to times 0.2 by 4. That will give us the answer of 0.8 newtons. So B would be the right answer. Another bit of practice for you. So with your paper and pen still, show you're working out. Pause the video and have a go. So in this question, I hope you haven't got tricked because you need the resultant force. So the first thing you need to do is do 3 newtons, take away 1 newton to work out the resultant force of 2 newtons in the forward direction. So our resultant force is 2 newtons. The mass of the car is 2 kilograms. So we know we've got 2 is equal to 2 lots of the acceleration. So the acceleration is 2 divided by 2, which gives us an acceleration of 1 metre per second squared. I hope you didn't fall for the trick in that one. So, Newton's second law. It's an equation that's all about resultant forces and the relationship between resultant force and mass, resultant force and acceleration. So we're going to have a look at how you could investigate those relationships. You could investigate Newton's second law in the lab. Here you can see the setup. The ramp has been raised to compensate for friction, and this is done by just slightly raising the ramp until the trolley is just about to roll down the ramp. You could use this equipment to check the relationship between the resultant force and the acceleration. To do this, you would need to keep the mass constant, and by that I mean the overall mass. So you would start with extra mass on the glider, and for each reading move the mass from the glider onto the hanger of hanging masses. And for each reading you would be increasing the force, but without increasing that overall mass. That means that we could find the acceleration. To do that, we'd use these 2 light gates connected to the data loggers. The velocity could be found at each place, and that would be done by measuring the distance of the card in meters that's going to block out the light, and program that data in. The computer will then time how long the light is out for in seconds, and it will also time how long it takes for the glider to move between the 2 light gates. So the calculation for velocity at each light gate can be found from displacement divided by time, and the acceleration can be found from the change of velocity divided by the time. And all of that would be done for you. This graph shows us that the resultant force is increasing, and as it does increase, the acceleration increases too. This is the resultant force increasing as acceleration increases for a fixed mass. The straight line also gives us more information. It's telling us that the resultant force is directly proportional to the acceleration. So if we double the force, we double the acceleration. If you push harder on the same mass, it accelerates at a greater rate. So back to our setup. We could also use this setup to investigate the relationship between mass and acceleration. This time the resultant force would be fixed, so we'd keep the same force on the hanger, but the mass of the glider would be changed. So the graph shows us that for a fixed resultant force, as the mass increases, the acceleration decreases. But we could take this graph further. By calculating 1 divided by the mass, we can plot a graph of the acceleration against 1 over mass for the same resultant force. Then we can see a clearer pattern. We can see that the acceleration is inversely proportional to mass. So if we double the mass, we're halving the acceleration. If you push with the same resultant force on a more massive object, it will be harder to accelerate it. So let's finish this video by applying our ideas to an exam question. Okay, first make sure you pause the video and read the question carefully so you know what you're having a go at. So we need to use the data in the table to prove that the family car does not accelerate as greatly as the sports car does, but that it does produce a greater accelerating force than the sports car. Don't just listen to my answer now. Pause the video, have a go at the question, and then check your ideas against my explanation to the answer to this question. So I'm going to deal with acceleration first. The sports car is accelerating at a rate that's double that of the family car because it takes 10 seconds to go from 0 to 30 metres per second for the family car, but only 5 seconds to make that same change of velocity in the sports car. I can actually calculate the acceleration, and I hope that's what you did. Acceleration is change of velocity divided by time. So for the family car, 30 divided by 10 will give us 3 metres per second squared. That's the family car. And 30 divided by 5 gives us 6 metres per second squared for the sports car. So I agree here, the sports car does have a greater acceleration. It's actually double the acceleration at 6 metres per second squared compared to 3 metres per second squared for the family car. And then to finish, we need to use F equals ma. First of all, the resultant force that I'm going to calculate is for the family car. 1,400 times by the 3 metres per second squared. Force, resultant force, is mass times acceleration. So the resultant force would be 4,200 newtons. For the sports car, it would be 600 times by 600 kilograms of mass by the 6 metres per second squared I calculated for the acceleration, giving a resultant force of 3,600 newtons. So I agree that the sports car does produce a smaller accelerating force. It's 600 newtons less than the accelerating force produced by the family car. I hope you found the video on Newton's second law useful, that you practiced your resultant force with your mass times acceleration. I hope you had a look at all the examples for yourself rather than just watching the video through in one go, and hopefully you feel a bit more confident about applying the ideas of F equals ma ready for the exams. I will see you again soon. Bye!
Regular review gets a better grade.
for you.
you.
Forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.